We have today our Bionics Institute, who will give us about transformation and changes, medical research on the physical and the mental health issue. Plus, our new member, Stephen, who is involved with emerging leaders for transformation as well. On both all of this, ASEAN Summit and RI's regionalization program, whether either will thrive or whether it will falter, whether our service will mean much to many or a little to few, whether Rotary is known with respect or seen as a real relic of days gone by, all this is up to us in a way, the Rotarians of Melbourne. But I call it a lesson in what we can achieve if we ignore the odds against us and if we are determined and never quit. Thank you.
Rotarians and guests, a toast to Australia and Rotary International. Australia and Rotary International. Please be seated. We will be breaking for lunch and we'll reconvene at 1:10 Please enjoy your fellowship and meal. Members, visitors and guests, it is my pleasure to welcome you to our 31st meeting of this Rotary year and our 5,022nd all-time club meeting in our 103rd year. It is wonderful to see you all here today. In celebration of World Hearing Week, today's meeting showcases our corporate member, the Bionics Institute, and their groundbreaking hearing research. Speaking today, we have CEO Robert Klupax and research engineer Dr. Winsley Hu. Also here we have the Bionics Institute Rotary designees Sam McLarty, Lucy Hooper and Joe Crowston. Would you please join me in acknowledging and making them all welcome? Thank you. We have other visiting Rotarians and guests of members. I invite you and your host to stand when your name is announced and ask that you remain standing to enable the club to welcome you in a collective manner. So the guests of Rotarians are Savindi Wiratanga, Bionics Institute, Lucy Hooper, Bionics Institute, Antoine Lahumi, from guest of Deb Vignew. Thank you all very much. Welcome. Great. So just some notices for everyone to be aware of. The footy tipping kicks off pretty much tomorrow, 7:30 p.m. So please join online through the link that you've received. If you've had any challenges in putting in your selections for this week, there are a number of members here who are able to help you. So there should be a fascinating year for that as well. Young Achievers Award, end of month also for nominees. So please speak to your networks, and there are lots of people out there who have been wonderful young achievers, and it's a great opportunity to recognise them. On the Thursday, 4th of April, we have been invited by the Walter and Eliza Hall Institute for a visit and a discussion about how Rotary and Australia's premier medical research organisation can work together, both to assist them in their research activities, but also in their clinical trials in the Pacific Islands. So this is a great opportunity to take some of our competencies and WEHIs and work together. So we'll put a note in the bulletin as to how to register for that. It'd be great to have an attendance of a dozen, if not more, as the WeHi group are also very thankful for the support they've received from Rotary Melbourne. Just as a side note, their former head is now chief of the CSIRO, Doug Hilton, and he will be speaking just before Anzac Day to the Thomas Baker oration. So he will be our orator. And now it's my pleasure to call on our guest speaker, CEO of our corporate member Bionics Institute, Robert Klupax. Welcome.
Good afternoon. Thanks very much, Chris. It's a great honour for us to be here today. I'm looking at the audience and you're all pretty familiar faces, and you're probably sick of the story, but as my head of development tells me, if you keep repeating it, people remember it much better. So thank you for the opportunity to talk again. It's really important that we speak today because, as Chris mentioned, it's Hearing Day. We are a world leader in it, and we are very passionate about reminding the populations around the world about how important, as a sense, hearing is, and when you don't have it, how your life changes. Today I'm going to give you a brief presentation to remind you about the work that we do, and then I'm going to hand over to one of my key, I like to call her superstar researchers, to talk about a particular program that we're doing in hearing loss research. After that, before we ask her some questions, we're going to share with you an interview that our newest member of Rotary, Sam McClarty, did a few months ago with a person with hearing loss who's become an ambassador to the Institute, and I think you'll really like seeing that particular interview. And then, after that, we'll give you a chance to ask Ying-Ji some questions. Now, I'm going to try to make sure this works. Wrong way? Can we see that? Yeah. So this is my first slide. Many of you will remember when you came to visit us. I know many in this audience have, and the first presentation I gave here about 2 years ago. We started 37 years ago with the pioneering work of Professor Graham Clark, who developed the cochlear implant, which many of you are aware of has made enormous changes to many people, and also created one of the greatest companies in the world, Cochlear Limited. But since then, we've really taken the teachings and learnings from Graham about modulating nerves in the ear to create medical devices that modulate nerves in other parts of the body to treat a number of different diseases. And our whole mission isn't, we mentioned WeHi before, a great medical research institute who looks at discovery primarily. Our major issue is to take discovery and translate that into the clinical realm so they can get to patients much more quickly. Two great institutes, slightly different styles. They do great work, we do something different, but at the end of it, both of us want to do the same thing, which is to solve major problems of human disease. Wrong way. I always get asked this question, in these audiences, what is bionics? It's a strange name, but it really is just the interface between biology and electronics. And for us, it's primarily trying to use electricity to stimulate or record from the nervous system. What we work on is a number of different areas. We started in hearing research, as I mentioned before. We've now gone into all these particular fields, brain research, bionic limbs in the recent times, and you can read them for yourself. But the more we look at this, the more that we look at the nervous system and how it interacts with all parts of the body, we're finding that our particular devices that we look for one disease can be used in a number of different diseases. And our job is to continue to move them up, get them developed, and get them tested in a number of different diseases so that we can treat many different diseases. What we are very proud of is the areas that we work in are areas that are going to make a major difference. We work in the field of Alzheimer's disease, you see the numbers. We work in the field of chronic inflammatory diseases, we call that IBD, or Crohn's disease. But you look at the numbers that you have there for hearing, 1.5 billion people affected by that around the world. And many people just take it for granted that I'm getting old, I'm going to lose my hearing. It shouldn't be the case. It doesn't need to be the case. And what we want to do is change that. And you'll hear from Ying Ji, we're working a lot with devices, but you'll hear from her a particular project that we're working on that hopefully will give people their hearing back. As I said, we've been working for 35 years. 4 major projects that we work on. We're working on cochlear implant improvements. Very proud of that. We're continuing to work with Cochlear as a contractor. In the top left-hand corner, we're developing much better techniques for detecting deafness and whether or not children who have hearing loss can have their hearing improved by intervention. You can imagine if you're a parent with a young child that's been diagnosed deaf, you want to know the interventions are working, children can't speak, and so bad things can happen. This particular technique we've been able to develop means that a clinician can see the effect of intervention using brain signalling without the child having to speak, which makes a great change. We mentioned to a couple of people before, and you've heard a presentation from my colleagues about tinnitus. Again, a major problem. I suspect there's a few people in the room with that disease. Our research has moved remarkably fast in the last 2 years, and hopefully by next year we'll have a clinical trial looking at a new diagnostic for tinnitus alongside a potential treatment that goes with it. And lastly, in the top bottom corner there is my colleague Ying Ji Yi, who leads a program looking to develop a particular type of drug delivery of a particular type of drug into the ear to effectively grow back the nervous system so that people can hear again. And without further ado, I'm going to hand over to Ying Ji, who's going to take you through what she's doing. But before I let her come up the stage, I want to introduce her a bit. One of the other things that we want to do at the Institute is be able to recruit the very, very best. Ying Ji came from China 8 years ago to do a PhD at the University of Melbourne with one of the world leaders in chemical engineering. He developed a technology that you'll hear about delivering drugs. She was a PhD in that lab. She came across to work with us at Bionics Institute, has been there for the last 3 years, and under her guidance, this project has moved dramatically on the cusp of clinical trials. I'm going to hand over to Ying Ji now to take you through it.
Thank you, everyone. It's a great honor to be here to present our team's work. Oh, that's a photo of me. All right, is it better? Yep. Today we're talking about hearing loss. So you can see here, according to WHO, there's 1.5 billion people around the world are currently suffering from hearing loss. And this number can go up to 2.5 billion by 2050. And among those people, around 60% of them, their hearing loss is caused by aging or exposure to noise. Those people with their hearing impairment, they could be suffering from social isolation, loneliness, depression, cognitive decline, even dementia towards the older age. Very sadly, there's no drug available to treat them, to help them. So as Robert mentioned, we've been dedicated to develop medical implants, cochlear implants, hearing aids to help them, but those medical implants themselves doesn't really restore the hearing. There's nothing to treat them. So those people are actually suffering in silence. What we want to do now is to bring a change to this situation and bring a drug therapy, a drug treatment to these people. Before I deep dive into our research, I want to give a brief introduction on how we hear sound. So this is an image of our ear structure here. When sound wave comes through the ear canal, it reaches the eardrum structure and bring vibration. Those vibrations get amplified by the little bone structure in the middle, and then bring the vibration all the way into the inner ear or the cochlear structure. This spiral thingy structure there is called cochlear. So this cochlear is filled with fluid. When the vibration comes, it will start a wave in the fluid. a type of cell called sensory hair cells. It's little hair cells over there. I think it's like on the right bottom corner. So those hair cells can ride the wave, feel the movement, and change the signal into electrical signal and pass it through to the nerve fibers, the yellow fibers in there. And those fibers carry the signal all the way to our brain, so we hear sound. This little structure, this little hair cells there, they're very fragile, especially the connections between the hair cell and the nerve fibers. So this is a diagram of what's happening when hearing loss happens. When we are suffering from loud noise, or when aging happens, this could happen. There's connections between the hair cell and the nerve fibers will be disconnected, those little red dots there. And then after that, the nerve fiber will degenerate and slowly you lose them. It's kind of like when you disconnect the lead wire from a microphone. You just cut off the signal, it can't go into our brain. Like I mentioned earlier, there's no drug treatment to stop this process or even reverse this process. But researchers around the world, including us, have been working really hard to try to find a cure. And we've found this potential drug molecule called neurotrophin. It's a type of growth factor, also a type of protein. We know that when we deliver this type of protein into the inner ear, it can reverse this process, preserve the nerves from further damage, and then reconnect them to the sensory hair cells. But the challenging bit is actually, how do we put this drug into our ear? This image again, you can see our ear structure is quite isolated from the rest of the body. This bone structure, especially around the inner ear structure, the cochlear structure. So there's a very limited blood exchange. That means we can't simply take a pill or have an injection on the arm. The drug just simply can't go through to the cochlea. What we need to do is to directly put the drug into the ear. It's called local delivery. There's still issue with local delivery. If we directly inject the drug into our cochlea, you can see the drug can be very rapidly cleared from the system, from the cochlear environment. Also, the injection itself can bring some damage to the cochlear structure, could further damage our hearing. What we need now is something small that can fit into our ear, something safe that doesn't destroy the cochlear structure, and something that can continuously and effectively deliver the drug into the cochlea, into our inside of our ear. That's why our team, in collaboration with experts in University of Melbourne, it's not going. So can I have the next page? So we're collaborating with my former supervisor, Professor Frank Caruso, and we developed this very unique drug delivery system using nanoengineering. It's called nanoengineering because everything's happening in such a small scale. So the superparticles we can see here, they are porous silica particles. It's kind of like a volcanic rock you can see here. It's porous, so the drug can stay inside, but they are in the size of a very, very sharp pencil tip. If you look further on the surface of the superparticle, they're not smooth. They are made of a lot of smaller particles. They're called nanoparticles. So can we have the next click, please? Thank you. So these are the image of the nanoparticles. If you're looking further, individual of those nanoparticles have porous structure. So next page is a section of this particle. We can see they have pores, bigger pores, small pores, and those pores is where we put the drug. And all those tiny little nanoparticles put together the bigger superparticle. In each superparticle, there's actually 1 billion of the nanoparticle. and each of them have a lot of drug inside. So with this superparticle technology, we developed a strategy to actually deliver our neurotrophin into the ear. Next slide, please. So this is a diagram of what we're gonna do. We're gonna use a soft cannula, gently put the particle into the middle ear, closing to the cochlear structure, which is inside the ear, but outside of the cochlear structure. This image here might look scary. You have a syringe stuck in your ear, but it's actually a very safe procedure, very well developed. The ENT surgeons can perform this on the outer patient in the clinic. After we put the particles on the surface of the cochlear, it's in the specific area called round window membrane, we will use a hydrogel to secure our particle there. It will stay there for up to 2 months. During those 2 months' time, the drug can slowly come out of the particle, get into our ear, and the neurotrophins can stay there and repair our hearing. So we've tested this system in our preclinical models. We put this drug-loaded particles onto the damaged cochlear and then have a look at what's happening inside. We've seen the signal of drug. So the picture on the right-hand side is a section of the cochlear structure. You can see the light dots, those are the drug signals. After 2 months of treatment, we can still see quite strong signal of drug sitting around the round window membrane area, which is where the particle would deposit on. And the drug travels through the cochlear, went to basal membrane. That's where all the little hair cells lives. So the drug has arrived where it should be. And then we also have data proving those drugs have been doing their work, trying to reconnect the hair cells with the nerves. We've seen nerve survival data. We've seen the regenerated little red dots that's connecting 2 parts. So our preclinical study has been very successful, proving our system is working. Our next step is to move towards our first in-human clinical trial to really bring this technology from benchtop research all the way to a treatment in the clinic. We're expecting the first in-human clinical trial to start in the next 2 to 3 years' time, and it could really lead to the world first treatment for hearing loss. And last, our vision is someday people with hearing loss can simply walk into a clinic, receive a small surgery, and walk out with our superparticles in the ear, have their daily life, while the little particles are working hard to repair the hearing, and those people can finally enjoy a better life with their families and the people they love. Thank you.
That was a fantastic, I'm biased, but that was a fantastic presentation. The little video that we're about to show before we bring Yingji back.
Can you walk us through your hearing? What's your journey been so far?
Yeah, so obviously probably not the most typical journey of hearing loss. When COVID hit and I realised I was probably lip reading a lot more than I may have thought, I went and got my hearing checked, and yeah, straight away she was like, yeah, you need hearing aids. And at the time you think it's just the world's worst thing. I remember calling my best friends at the time, Alana and Kate, and I was bawling. I was just bawling my eyes out, and they were like, it's okay. Like, they were so happy for me. But I think as a person, you're just like, this is now the rest of your life. Knowing what I know now, I wish I could go back and got them earlier, because it's changed my life for the better, socially as well. I feel more comfortable in social settings, and so I hope that kids can look at my journey and sort of recognise what I've been through and notice that the stigma behind hearing aids has totally gone, and it's almost cool to wear hearing aids now, and I want to be a part of that journey with them. And I hope that I can be someone to help change that stigma as well.
So on the basis of Mackenzie's ambassadorship, my colleagues put together a major campaign to recognise World Hearing Day. We set ourselves a very bold target of $150,000 of donations, and I'm proud to say we reached $143,000, but we'd love to get that to $150,000. And the President said I should ask everyone in the room to see if we can top that up and ask your family and friends. That's all I was going to do from the pitching, but I want to bring Ying Ji back up to the stage because after that presentation, I suspect there's quite a few questions for her. So, Ying Ji.
Thank you.
Thanks.
And your English is fantastic for
thank you.
very wonderful communication. My question is, do you ascertain those people who are deaf as to whether their hearing can be restored? I imagine there are some who will never be able to hear. So I just wonder, how do you handle that?
Thank you for the question. That is very true. So great. Is it better now? Yeah, I have to admit, like every therapy, every treatment all have their limits. So the treatment that we are developing is based on the ground truth is there's still hair cells, that little cells sense the movement is still available in the ear. It could be like just a few of them left. So we can do reroute. The connection could be reroute to the nearby nerve. But if there's absolutely no hair cell left, there's very little we can do. So yes, that's true. We have to admit every therapy has a limit, but we believe this therapy has a very broad patient population we can help. Yeah.
Bruce Davidson. I'm going to walk away with a spring in my step today because I've just heard that hearing aids are cool. You all heard it too. They're cool. My question is, how do I get on the trial for treating deafness with a drug?
That's a great question. So as I mentioned earlier, we're working really hard to push this technology to first in human clinical trial. Our vision is in the next 2 to 3 years. And obviously, based on all the resource limitations, it could take a bit longer. But we will have newsletters announcing all our ongoing clinical trials and the clinical trial that's going to be started. So be sure subscribe our newsletters and keep an eye on what's happening with us. Yeah, we'll definitely make a call if this clinical trial start to recruit patients. Yep.
I have to ask the question, can it regrow hair anywhere?
Oh, I'm sorry to answer, but it's no.
Just a follow-up question, I guess, on the, how useful it is or how effective it is for people that have lost, got to the end of the journey. If it plays out in the best possible scenario, could this be like a preventative type of application rather than curative? Like when you get to a certain age, you have a few micro drugs injected to make sure you don't suffer from hearing loss?
Thank you. That's a fantastic question, actually. So we've been thinking about that. So I have to say all the results has to be supported by data, and all our current data is conducted on damaged cochlea. So we haven't tried the preventive method, but it's certainly something we can look through and look into. Because of this thing, we know it's progressive through aging and through exposure of hearing. So when it's onset, when just started, you probably don't notice you have hearing impairment, or you probably don't notice in your daily life. But at that stage, we could already step in to help already. But again, we will need to do further research on that front. Thank you.
Peter Rogers, can you just clarify for me the neurotrophin is the agent that you're using, and how do you measure the regeneration of the nerves? Like, have you done this through animal models, or can you actually make that measurement in a human?
Thank you for the question. We currently haven't started any human trial. That's what we are visioning in the next 2 to 3 years. So our current data is collected in our preclinical model, which is animal model. We've tried a few different species and have collective evidence showing once we have successfully delivered this drug inside the cochlea, it can regenerate the connections. We're doing some histology analysis to look at the cells at cellular level, and if this connection has been regenerated, if the nerve cells are surviving more than the group that hasn't been treated. Yeah, so we have evidence in animal model.
Robert, can I just ask a question, well, of both of you? In terms of partnering with other research institutes here and overseas, just from an intellectual property viewpoint, how does it work?
That's a really good question. So in this particular circumstance, the intellectual property, there's two parts. There was the delivery system, the volcanic rock type of delivery system that Yingji said that was first developed at the University of Melbourne. And then we took it to develop the neurotrophin, work out how to put it to regrow hairs. So there's patents filed around those two techniques combined, which we jointly own with the University of Melbourne and us. The neurotrophin itself, we're working with CSIRO to help us make it, and we've filed intellectual property around that. The next question is about how we commercialise that if we have to bring a big pharmaceutical partner in, which is the usual way these things get developed. We will do a licensing deal with pick a brand name company, Pfizer, Glaxo, Merck. They're all interested in this field. And what would normally happen is all this technology that we've developed, we're protected by patent, and then we would give them a license to those patents in return for money and their commitment to develop it and do clinical trials. That's how it usually works. There's another model in between that we like to use at the Institute, which we're going to take our intellectual property and we would sell that into a new spin-out entity, raise money from angel investors and venture capital, and with some hope, that company itself would be the company that develops the technology all the way to the clinic, or it could do that in partnership with a major pharmaceutical company.
So presumably the lawyers are making money all the way along the line, are they?
Yeah, well, we were talking earlier today about how much this patent portfolio has cost us, just us. It's $300,000 to date. And looking forward for the next 10 years, we're budgeted $1 million, and that's just the patents. And anyone in this room who works in the field thinks one patent's enough. This type of technology in the field of pharmaceuticals will probably finish up with 400 or 500 patents around it. And so if you think of the drugs that you're taking now, the amount of money that's being developed, the cost to develop is multiple millions of dollars, but the patent portfolio that underpins any drug that you're taking would probably be $10 to $20 million a year.
Oh.
So we talk about all the research we need to fund, but if you don't protect it, it's worthless. But to protect it costs a huge amount of money as well.
Thank you. I have a question. These neurotrophins, one of the issues we all face is the cost of healthcare. So are these chemicals, aside from the delivery, are these chemicals likely to be expensive? I don't see, you say CSIRO's making them. Is it likely to cost a fortune or?
You
Okay.
You go first, I'll go second.
All right. I don't know about the detailed quanta, but what I do know is we've developed our own manufacturing strategy, has significantly bring down the cost compared to a more traditional manufacturing method that will cost more. So we've, I believe we bring it down more than half, way more than half actually, the initial cost. But in terms of the quanta, I probably hand over to Robert.
Yeah, so a really good example, looking at the audience here and the age, if any of you have macular degeneration and have to get the injections into your eye, you get those injections once or 3 to 6 times a year. Each one of those injections will cost you $290, but cost the government $2,000. So a course of therapy for those drugs into your eye each year is about $20,000. We're thinking with this particular therapy, looking backwards, what we're hoping is we can be selling it for a course of therapy once a year, $10,000 a dose, but you'll get your hearing back. And we think that's actually, given the way a lot of these drugs are being sold for and the price is very cheap, compared to what they've got, but still, it's not going to be inexpensive. But the question we will need to justify is the value that we give to someone who gets their hearing back. Is it worth paying the money? And that's the way these things work. We're very certain that if I walked up to anyone in this room who had lost most of their hearing and said, I can give you your hearing back, what would you pay? The $10,000 a year would be a pretty cheap price to pay.
Got time for another one or two quick questions. Oh, where's Bob? I was going to get you to walk up, Bob, but I won't do that. There you are.
I live in Albert Street, so I frequently walk past the Institute building. It's very small. How the hell have you achieved so much being such a small organisation? It is a remarkable series of achievements.
Well, we've been going for 36 years, but we're not just in that building in Mollison House in Albert Street, Bob. We have our labs also in St Vincent's Hospital, but we are small. And one of the great things that we're proud of, Chris mentioned Weehai. Weehai has, Chris, 1,400 people, I think. We have 90. And so to have the yield that we've had, we're pretty proud of that. But my goal would be to have these type of people, 10 Ying Gs, imagine what could happen. And that's part of the reason I'm out here talking to you and everyone else. We need the support to bring this talent, and when you bring the talent together, I think great things can happen. And to your point, it's quite amazing. The newest, shiniest buildings don't always get the greatest outcomes. It's the people in the buildings that make it. Don't get me wrong, I try to give them a good environment, but it's the talent that's there. And really, I think it's the passion of the people that we've got, Bob, is why we've been successful and continue to be successful, and also because they're just so talented.
Last question.
Now, Robert, you spoke about bionics being biology and electronics. This project doesn't appear to me to have any electronics involved.
There is.
In it. I was just wondering, how does this become a bionics project?
Good question. So it definitely fits in the biology part. The protein itself is a very it's a type of protein. But the hidden electronic part is during our manufacturing process. We're using this very unique process called spraying or electrospinning. What it does is to assemble this little tiny nanoparticles into the superparticle structure. So this step is quite unique, protected by our patent, and using this electrospinning process, which is the expertise of our institute. Yeah.
Thank you very much.
Thank you.
That's right. What I'll do is I'll get you to stand here for a moment, and maybe it was the photo op. So thank you very much. I think what we're hearing is that you will look after our hearing, but Rotary also has some secret sauce. We will look after your feet. So we have some socks for both of you, some very rare 2023 convention socks made by our past president, Bill Endersby's company. 200% Australian owned, lots of love as well as Australian materials. Thank you both very much. This is not a goodbye or anything like that, because as we have the Bionics Institute as our corporate member, we will have a lot of relationships with them. And we believe that Rotary can also assist in putting the word out to a lot of our community, both the young as well as the older, that have hearing issues, but that also want to participate in funding of research and in increasing awareness across our community. So thank you both very much.
Thank you.
And we look forward to working with you. Thank you. All right, so thanks to all our visitors and guests for attending. Thanks also to our latest golf sensation MC, past President Peter Dakin, and for the reflection from Ruth Carlos Martinez, and our lunch setup team and reception teams for their efforts. Reminder, next week is our monthly evening meeting. This month we're meeting at Monash University, Clayton, a visit to the Bio Eyes project. Now, details will be in the bulletin, but what is the Bio Eyes project? It's about encouraging STEM education in the young. So when I was looking at this, I was fascinated because we're talking about students during this program will be nurturing the development of zebrafish embryos, little fish, observing their transformation from a fertilized egg to a free-swimming larvae. Students will be studying lifespan and development of zebrafish, their anatomy and genetics. How cool is that? We didn't have that in our time. But I think it's a testament to the innovation, to the deep intellect and smarts out at Monash University, and connecting with what the future requirement is for our nation, as well as for the region and globally, to get more kids into STEM. So it'll be a fascinating program, and look forward to joining us all there. Details again in the bulletin, and now we kindly ask that you please stand.